pH and strong acids. You might remember that the pH is a measure of the hydrogen ion concentrations. You can calculate it by taking the negative log of the hydrogen ion, using your calculator, of course. And a compact way to represent solution acidity is the pH, because if we have that number, we can discuss how acidic or basic a particular solution is. As the amount of hydrogen increases, the pH decreases, because, of course, the more you have, the smaller the exponent, and thus the smaller the pH. When you write pH, remember the number of decimal places in the log is equal to the number of significant figures in the original number. pH, of course, goes from 0 to about 14, pH of 7 being neutral, pH greater than 7 being basic, and pH less than 7 is acidic. The higher the pH, the more basic; the lower the pH, the more acidic. Here's a chart of common pHs for different substances. You can see in the neutral range, water, blood is slightly basic, milk is slightly acidic, etc., all the way down to stomach acid, which has a pH of about 2, and household ammonia, which is a cleaner, has a pH of about 12. So let's look at some examples of calculating pH. Alright, so the first one, 1 times 10 to the negative 4 molar hydrogen ions. That's pretty easy. I could use my calculator if I wanted to, but because it's 1 times 10 to an exponent, all I really have to do is look at the exponent. In this case, you notice the exponent is a negative 4. So that means the pH is 4. And let's see if this is going to show this to me. Yep. And 0.040 molar OH negative ions. Now, later on in this slide series, we're going to see about POH. And personally, that's the way I like to do it. Remember, if you go from pH to hydrogen ion concentration, how do you go from there to there or backwards? Well, if I have hydrogen ion concentration and we go to pH, we take the negative log of the hydrogen ion concentration, and that's the pH. And to go the other way, we say 10 to the negative pH, and that gets us to hydrogen ion concentration. We can also go POH to the concentration of OH negative, and back. Here, negative log of the hydrogen ion concentration, or 10 to the negative POH. What are the other two numbers? Again, future slides will show this, but hopefully this chart you will remember from intro. We know that Kw brings together hydrogen and OH negative, and of course you know that's 1 times 10 to the negative 14, or pH plus POH equals 14. So anywhere we are along this continuum, we can find another piece. So I guess what I'm saying is I know the OH ion concentration right here, and I would like to get the amount of OH, or actually the pH, pardon me. So what I could do, let's see if it works in the calculator. If I take the negative log of 0.04, well, negative log 0.04, I get 1.397 and some other decimals. I only need 3 sig figs here. Actually 2, about 1.40. Then what I can do is I can say 14 minus 1.397, that, and I get about 12.6. So let's see what they say the pH is. Yep, exactly. So this is probably the easiest way to do this particular problem. I'll review. Alright, the pH of a solution is 5.85. What's the hydrogen ion for this concentration? What's the hydrogen ion concentration for this particular solution? I want to get pH, and you're going to take negative log of, or you're going to get hydrogen ion. So you're going to say 10 to the negative 5.85. When we do, we get about 1.4 times 10 to the negative 6, as this suggests. Notice you get a ballpark answer if you just look here. 5.85, making it negative, is about negative 6. So approximately, that's one way to kind of eyeball the answer to make sure you're getting about the right thing. Now, we already talked about Kw being hydrogen times hydroxide, and pH plus POH is Kw, or pKw as they're saying here. And so that's how we get that. And in the previous diagram that I drew, which put together OH, H, pH, POH, you can see how these things are related. So there's going to be more calculations. Calculate the POH for each of the following solutions. Alright, 1 times 10 to the negative 4 molar hydrogen. Well, we already know that the pH of that is 4. And so the POH of that would be 10, because of course 10 plus 4 is 14, which is the Kw. And the 0.040 molar OH, the POH, pretty easy. It's just the negative log of that, and that's about 1.40. Another question, the pH of a solution is 5.85. Sounds familiar, I think we just did this. What is the OH concentration for this solution? So this is pretty easy. You could either you could get the hydrogen ion concentration and use Kw. You could get the POH and then take that and put that 10 to the negative POH, and when you work it all out, you get 7.1 times 10 to the negative 9. Very easy, very straightforward kinds of questions. So let's think about acid-base problems. One of the things you're going to really have to think about is something a strong acid or a weak acid, or, as the book will say, what are the major species in solution? What is the dominant reaction that will take place? Is it an equilibrium reaction or a reaction that will go essentially to completion? In other words, equilibrium reactions means that they are weak. Go to completion means that they are strong and that they ionize 100%. So that's what you have to figure out first. Recall all major species until you are left with an equilibrium reaction. React all major species until you are left with an equilibrium reaction. Pardon my hat. It seems to be wanting to jump off of my head. And then solve for the pH if needed, and of course if the question asks for it. So consider a solution of 2 times 10 to the negative 3 molar HCl. Now you will have to memorize the strong acids. You can find those in your book. HCl happens to be a strong acid. So what are the major species in solution? In other words, once it's dissolved in water, what are the major species? Things that are strong acids will ionize, therefore they produce ions. So the major species are, of course, the hydrogen ion, the chloride ion, and water. Water doesn't ionize well. And what is the pH? Well, because HCl ionizes 100%, the concentration of HCl is equal to the concentration of hydrogen ions and of chloride ions, but we care about the hydrogen ions. So the pH is going to be related to the concentration of HCl, which is 2 times 10 to the negative 3. So if you do the negative log of 2 times 10 to the negative 3, you should get 2.70. Calculate the pH of a 1.5 times 10 to the negative 11 molar solution of HCl. Alright, well in this case, if you did the pH like we normally do, in other words, we take the negative log of 1.5 times 10 to the negative 11, I get 10.8. And you'd say, okay, that's the pH, but how could that be? 10.8 is a base, and HCl we know is an acid. Well, don't forget, the other part of the species that are in solution besides hydrogen and chloride is water. Water has a hydrogen ion concentration of 1 times 10 to the negative 7 because of Kw. So that actually is the major component of, or the major contributor of hydrogen ions. It's more concentrated than the one you see here. Therefore, the pH is going to be 7. So even if I wanted to use my trusty calculator, which I just did, and I got 10.8, I knew that couldn't be. So there must be something else that's a major contributor of hydrogen ions. In this case, it's the water. Usually that's kind of an unusual situation. But here's an example where a strong acid, a weak enough strong acid, actually has a pH equal to that of water, because it's so dilute. Alright, calculate the pH of a 1.5 times 10 to the negative 2 molar solution of HNO3. Well, HNO3 is a strong acid. It ionizes into hydrogen and nitrate ions. And for this, I think all you have to do, it says when H3 is added to water, it takes place immediately. That means it's strong, and you can see the reaction here. The other choice would be some kind of reaction like this. Well, this doesn't happen because what controls the pH? Here's the self-ionization of water, and in aqueous solutions, this reaction always takes place with all reactions. But what's the major contributor of hydrogen ions? Of course, it's the nitric acid. So in that case, we just take the negative log of the hydrogen ion concentration from several slides ago, and we get 1.82.